Welcome to Learning Outcome 4, where we step back and look at the whole business of doing statistics well, from asking a good question to drawing an honest conclusion. This is where everything from the earlier outcomes comes together on a real investigation. Good statistics follows a cycle: plan, collect, process, interpret, and then, if you need to, refine and go round again. It starts with a clear question or hypothesis and ends with a conclusion the data actually supports. Each stage leans on the one before, so poor data collection can't be rescued by clever processing later. Garbage in, garbage out, as they say. This whole outcome walks through that cycle, using the tools we built up in outcomes 1 to 3. Let's name the stages. First, pose a hypothesis, a clear, testable claim to investigate. Second, plan and sample. Decide what data to collect and how to gather it fairly. Third, collect the data through surveys, experiments, or existing records. Fourth, process it, organizing and summarizing with tables, averages, spread, and charts. And fifth, interpret and conclude, judging your results against the hypothesis and being honest about the limitations. 5 clear steps, and we'll dig into each. Everything starts with a good hypothesis, a statement that data can either support or reject. A strong one might be, students who revise more than 10 hours score higher marks than those who revise fewer. Compare that with a weak one, like revision is good, which is far too vague to test. A solid hypothesis names the variables and suggests a comparison or a relationship, and you collect data specifically to test it, not just to see what happens and hope something interesting turns up. A quick bit of vocabulary. The population is the whole group you're interested in, say all the customers of a shop. The sample is the smaller group you actually study, chosen to stand in for the population. The sampling frame is the list you draw your sample from, like a membership register. And bias is any systematic error that makes your sample unrepresentative. Getting these terms straight matters, because sampling is where investigations most often go wrong. Why bother with a sample at all, rather than studying everyone? Because studying a whole population, a census, is usually too costly, too slow, or just impractical. A well-chosen sample gives you reliable conclusions for a fraction of the effort. The catch is that the sample must genuinely represent the population, or your conclusions will mislead you. And what protects you there is the method you use to choose the sample. There are several standard sampling methods, each with a watch-out. Simple random gives everyone an equal chance using random numbers, but you need a full list of the population. Systematic takes every nth item from a list, though hidden patterns in the list can bias it. Stratified samples each subgroup in proportion to its size, which means you need to know those sizes. Quota fills set numbers from each group, chosen by the researcher, where personal choice can creep in as bias. Cluster samples whole groups at random, like entire classes, but clusters may differ from one another, and convenience just uses whoever's easy to reach, which is quick but often unrepresentative. It helps to split those into 2 camps. Random methods, random, systematic, and stratified, give every item a known chance of selection, which reduces bias and lets you generalize to the population, though they usually need a sampling frame and more effort. Non-random methods, quota and convenience, depend on the researcher or on ease of access. They're quicker and cheaper, but carry a higher risk of bias, so their conclusions need treating with more caution. As a rule, if you can manage a random method, your findings will stand on firmer ground. Let's work a stratified sample. A college has 480 Year 12 students, 320 Year 13, and 200 staff, 1,000 people in total. We want a sample of 50, keeping each group in proportion. For Year 12, it's 50 times 480 over 1,000, which is 24. For Year 13, 50 times 320 over 1,000, that's 16. And staff, 50 times 200 over 1,000, which is 10. Check the total. 24 plus 16 plus 10 is 50, and each group keeps its fair share of the sample. Size matters, but it isn't everything. Larger samples give more reliable results, though they cost more time and money, while too small a sample is easily thrown by a few unusual responses. Watch out for the classic sources of bias: an incomplete sampling frame, leading questions, and non-response. Surveying only shoppers on a weekday morning, for instance, quietly misses everyone at work, and that's a biased sample. Aim for a sample that's large enough to be representative and chosen by a fair method, because a large sample chosen badly is still biased. Method beats size every time. Before processing, it helps to know what kind of data you're holding. Primary data is collected firsthand for your own investigation, like your own survey. Secondary data was gathered by someone else, such as Office for National Statistics figures or company records. Qualitative data is descriptive and non-numerical, things like color or opinion. And quantitative data is numerical, either discrete, meaning counts, or continuous, meaning measurements like height or time. Knowing which you've got steers how you can summarize it. Processing is where the tools from earlier outcomes earn their place. You organize raw data into frequency tables and tallies. You summarize the center with the mean, median, and mode from outcome 1. You summarize the spread with the range, interquartile range, and standard deviation, also from outcome 1. You show relationships with scatter diagrams and correlation from outcome 3. And you display it all with suitable charts, bar charts, pie charts, histograms, and cumulative frequency curves. Choosing the right chart makes or breaks a report. A bar chart is best for comparing categories, like survey responses. A pie chart shows proportions of a whole. A histogram displays the distribution of grouped continuous data. A scatter diagram reveals the relationship between two variables. A cumulative frequency curve is for estimating the median and quartiles. And a box plot is ideal for comparing spread across groups. Match the display to the question you're answering, and the pattern jumps out. Let's process some real survey data. 100 people are asked how often they shop online. Never 12, sometimes 28, often 34, and daily 26. We've already got the frequency table, so convert to percentages, and because there are exactly 100 people, the counts read straight across. 12% never, 28% sometimes, 34% often, and 26% daily. The modal response is often, the highest frequency at 34. And combining often and daily, 60% of the sample shop online, at least often, a headline figure, a bar chart, would show off nicely in a report. Turning that frequency table into a bar chart makes the pattern instant. The height of each bar shows how many respondents chose each option, so the tallest bars, often and daily, clearly dominate. A reader grasps the shape of the responses far faster than they would from a column of numbers. Just be sure to label both axes and give the chart a title. An unlabeled chart tells the reader nothing. A good chart does a lot of the interpreting for you. Real processing almost never rests on a single technique. A typical write-up combines several: a frequency table one or two averages, a measure of spread, and a chart. If you're dealing with two variables, you'd add a scatter diagram and a correlation coefficient on top. The skill isn't using every tool available, it's choosing the ones that actually answer your hypothesis. Restraint and relevance beat a scattergun of every chart you know. Interpretation is where you link the processed data back to the hypothesis you started with. State plainly whether the evidence supports it or rejects it. Back that up with the actual figures, your averages, your spread, your correlation, not just a vague impression. And be honest about how strong the evidence really is, because statistics very rarely proves anything outright. It weighs the evidence. Let's draw a conclusion properly. Our hypothesis: students who revise more score higher marks. A sample of 30 students gives an R sub S of 0.78 between revision hours and marks. That's a strong positive correlation, which supports the hypothesis. On top of that, the mean mark of students revising over 10 hours, 68%, comfortably beats those revising fewer at 52%. So the evidence supports the hypothesis for this sample. But note the limitation honestly. 30 students from one college may not represent all students, and we should avoid claiming revision alone causes higher marks. Other factors surely play a part. Two words you'll want in your conclusions are reliability and validity. Reliability asks whether you'd get similar results if you repeated the study, and larger, well-chosen samples are more reliable. Validity asks whether you're actually measuring what you set out to measure. Sources of error include biased sampling, leading questions, measurement mistakes, and non-response. And here's the reassuring part. Acknowledging your limitations makes a conclusion more credible, not less, because a good conclusion states its finding and its limitations together. This cycle isn't academic. Organizations run on it. A supermarket surveys its shoppers, processes the responses, and adjusts which products it stocks. The Office for National Statistics samples households to estimate unemployment and inflation for the entire UK. In each case, they present conclusions clearly, with supporting figures, a chart, and an honest note on limitations. And then the cycle starts over, with a sharper question the next time round. Let's sum up Learning Outcome 4. The data handling cycle runs from a testable hypothesis through sampling, collection, processing, and interpretation. Sampling methods include random, systematic, stratified, quota, cluster, and convenience, and the method you choose is what controls bias. A stratified sample takes each subgroup in proportion to its size, so 50 times 480 over 1,000 gives 24 from a group of 480. Processing combines frequency tables, averages, measures of spread, correlation, and suitable charts. And interpretation tests your results against the hypothesis while stating reliability, validity, and limitations honestly. So that's the full statistical cycle, the framework that turns a question into a defensible conclusion. If you'd like to strengthen the sampling and design side, Rowntree's Statistics Without Tears explains bias and representativeness in plain language, and the Office for National Statistics website shows the whole cycle running at national scale on real surveys. The Royal Statistical Society's case studies on sampling and opinion polls are well worth a look for how this plays out in practice. Best of all, plan a small investigation of your own, a survey of your class perhaps, and take it right through the cycle before you tackle the assignment.